What's up? Are we live? Are we live YouTube? Yeah, seems nice, seems good. Um, is the chat working? Uh, yeah, seems good. Um, this is good. So I can see also the concurrent viewers, chat rate views. That's pretty cool. Yeah. So yeah, I'm back streaming, guys, and after a long time, almost a year, I got all the views still here. Ignore the mess, but so this is like a 5070 Ti GPU and like a good CPU. I sell bought a good CPU. And also, change the colors of the models. Seems cool, right? Yeah. So, yeah. Hope so now nothing lags. Like, to stream on that laptop you see there. It's almost 8 years old. It's quite, quite a challenge. And yeah, now it's good. Just pieces here. So this is a new system, and also dual booted it with like Ubuntu, which I used to stream the Carla engine, right? So I'm interested to get into it a little bit to see what can I do with it. So that will be one of the next streams. Today just a chill stream, and I'll be working on like not working, but just check it out, the Llava models. I'm gonna get into the VLM field, see what it actually is. So yeah, let's see. So I can change the scene. That's cool. Yep. Oh, okay. Yeah. So now that we can see this screen, this is nice. So let's plan something. What do we need to do today? Firstly, we want some nice music in the background. So this is Obsidian, which I use a lot, as you can see here. So it's basically a local, like it lets you use the local .mbs. So all these are .mb files, and so it's all of your data is local. You don't have to push anything to the the cloud like Notion does. So this is good. Let's get some nice.
Running a business isn't easy.
Sorry, I don't have a premium.
Tons of paperwork, but having the right tools.
That's good. And this is done. Let's get Yeah, so I'll show you guys. Let's and this is the paper. This is the Git repo. This is the main one. Yeah. So can I keep the chat somehow on the screen? Maybe this. Oh no, I cannot. Okay. Yeah, let's keep it like this only. Yeah. So so this was the paper I was checking out. And this was like the one of the first vision language models of like open source papers. Um, and if you look at the abstract, um, so instruction tuning large language models using machine generated instruction following data has been shown to improve leadership capabilities on new tasks. But the idea is less explored in the MIT model field. So instruction tuning is basically so we have a base language model, right? And uh, like once you have the base language model, you have to like start fine tuning it to get different actions from it and like different structured outputs from it because it will just start creating text, right? It doesn't know where to stop. It cannot understand your commands, anything like it. So instruction tuning is done to get like different characteristics out of that language model. And this was the first try, I think, on the this thing, the vision side. And they use GPT-4 to generate language image instruction following data. So language only GPT-4 is basically it takes the vision input, but I think it creates language out of it. Like only the modality on the output is only language, if I'm not wrong. Let me check. Was GPT-4 language only? Yeah, it was designed as a yeah. So it was not language only in terms of input. So to generate multimodal language image instructions, data by instruction tuning on such generated data, we introduce Llava, large language and vision assistant, and end-to-end trained language model. So, so they created two benchmarks. Okay, so there was a version of GPT-4 which was only language. Um, yeah. So let's first check out how this thing works. Stat. the model working. So if we check out the terminal, um, yeah, and let's see string projects all good, right? Yeah. So here, um, let's create a directory Llava CD into it and uh, open it with cursor. So I've been using cursor also recently, which seems very nice. Um, so let's look at Llava point 6 Hugging Face. Yeah, so this is 34 billion. I think 34 billion we cannot run locally. So 7 billion, yeah, mystery. This I think can be run locally. Let's check this out. Prompt template. I think let's use this one. Um, Model of by Luis. So importing the Lava Next processor. The Lava Next model, I think they call it. Yeah, Lava Next model. So this is the next paper, I think. Improved reasoning, OCR and more knowledge. So this was Lava 1.5 and so Lava Next. Let me search. This paper. When is this paper from? Okay, okay. This wasn't a paper, I think. Or was it? So Lava Next. This was released on 2024 uh, May. Okay. So we have this Lava one game face. Let's see. Can't I run the original Lava? So this is it, I think. 1.5. We ask ChatGPT then. Can we run Lava, the original weights released now? Mm, This is the official. Okay, let's just go with what we have right now and just check this later. I think we can run the 1.6, the latest one. Let's try this out for now. We'll get back to what they're saying later. So let's first activate it. Yeah, so here also is that yeah, and now I go Python model.py. So they are using Torch, PL, Pillow, request library. With the next processor, they're using this. So I have it. Oh, I used it before, so I have it. Lava next for conditional generation from pre-trained. See what this is doing. Low CPU memory usage is true. Nice. Okay. So this is, I think, a image on the internet. Yeah, so this is what we are working on. And we open it using request library. Let's see. And then what is shown in the image. Let me start another bit bash. Let's see if our GPU is running. Oh, crazy. 100% memory used. 16 GB VRAM and 0% here. It's okay, it will work, I think. By the way, is the quality all good of the stream? It seems good to me. Yep. And what happened to our music?
This is your brain when you're struggling to focus. And this is your brain when you're in the zone.
Did you guys watch this Andre Karpathy podcast, by the way?
This is the best way, but I almost kind of feel like, again, making these analogies, imperfect as they are, we've stumbled by with the transformer neural network, which I think is extremely powerful.
It seems like
Very
it's talking
general.
in
You can train
2x.
transformers on audio or video or text or whatever you want, and it just learns patterns, and they're very powerful, and it works really well. That to me almost indicates that this is kind of like some piece of cortical tissue. It's something like that, because the cortex is famously very plastic as well. You can rewire, parts of brains, and there was the slightly gruesome experiments with rewiring like visual cortex to the auditory cortex, and this animal like learned fine, etc. So I think that this is kind of like a cortical tissue. I think when we're doing reasoning and planning inside the neural networks, so basically doing reasoning traces for thinking models, that's kind of like the prefrontal cortex. And then I think we maybe those are like little check marks, but I still think there's many brain parts and nuclei that are not explored. So maybe, for example, there's a basal ganglia doing a bit of reinforcement learning when we fine tune the models on reinforcement learning. But whereas like the hippocampus, not obvious what that would be. Some parts are probably not important. Maybe the cerebellum is like not important to cognition, it's thought. So maybe we can skip some of it. But I still think there's, for example, the amygdala, all the emotions and instincts. And there's probably like a bunch of other nuclei in the brain that are very ancient that I don't think we've like really replicated. I don't actually know that we should be pursuing, the building of an analog of human brain. Again,
Oh, I think so. Let's see. Where is ChatGPT? How much RAM would the Llava next 7 billion need? So give me that calculation. Let me stop this. I think it's taking a lot of time. So is there a bits and bytes config for this? Yeah, this is it. 4-bit. So I think I have it here. Hmm. So let's drag this. Eight bit and this. Okay. So this is the model. We don't want this. And what else was there? And this should work, I think. Yeah, so yeah, 14, 16. I think because the OBS is running and all the things are running, it's taking a little bit more time. But I did try it out without the 8-bit quantization, and it was running, but it takes a lot of time. So um, now I think, see, look, we just look at it again. Yes, it already worked. What is shown in this image? The image appears to be a radar chart, which is a type of multidimensional plot that displays data points on axis starting from the same point. The particular radar chart is showing the performance of various models of systems across different metrics. So MMWet, MMWet QA, squad. Is that right though? Yeah, that is quite nice. It is very impressive, right? For a vision model. So let's see what it actually does. Uh, let's first look at the calculation for this. So this was the 1.6, right? Mm-mm-mm. Log. Yeah, stronger supercharge. This. Okay, this one. Yeah. So we ramp it down. 7B at batch 1. Single image generation, no training. So number of LLM parameters 7 to E9. Okay. So 2 FP16 188 0.54. 32 to into H elements, 0.5 MB. So I think it runs 0.5 MB plus 14 GB, right? And mine is 16 GB VRAM, so it should run. Yeah, that is good. So now that this is running, let's see how the basic Llava actually works. Oh, let's first get a brief description from ChatGPT. Can you? Yeah. So okay. Yeah. So data generation. They start from existing image text pairs, right? So let's get the paper also on the side. Um, yeah. So this thing. So they get the yeah. This is it, right? So for an image X and its associated caption XC, it is natural to create a set of questions XQ with the intent to instruct the assistant to describe the image content. We prompt GPT-4 to curate such a list of questions. Therefore, a simple way to expand an image text pair to its instruction following version is human. So you get the XQ, which is a set of questions given by humans to start it. Then XV is the actual image, stop, and then assistant creates a XC, which is caption. So, okay, so it lacks in-depth reasoning in both instruction and responses. So, to create instruction following data involving visual content, specifically in order to encode an image into its visual features to prompt a text-only GPT, we use two types of symbolic representations. Captions typically describe the visual scene from various perspectives. Bounding box usually localize the object in the scene, and each box encodes the object concept. Okay. Uh, so they use the Coco dataset. Um, I think it has the like 100 different classes, 200 different classes, I think, and three types of instruction following data. One example per type is shown. So we design a conversation between. But how are they using text-only ChatGPT? So okay, let's use Coco, which has image and caption pairs or annotation. That's fine. They encode the image with simple symbolic representations that a text-only LM can consume. okay, which is captions, bounding box, object labels, spatial coordinates. Okay. So object label, bounding boxes, spatial coordinates, everything is given as a context to the LLM. Then they prompt the text on the LM with the symbolic representation, a manually designed C instruction. The LM generates responses. This processes many instruction image answer triples. But I think this is a very limited kind of view, a way to teach. But I think how like fit the bounding boxes and the context and captions, I think um, they get like a big data set created without having to have a human annotate everything, which is good to actually like for the basic instructive tuning. Uh, so multi-done QA about the image. Okay, this is what they sampled from the GPT-4. That is a singleton but real description of the image. Singleton require reasoning about the image. Acha, this is the model architecture, but one sec. So, um, right. So, where's the ablation? So, okay, yeah. So this is the context. So we have the captions like this for this image. Um, we have context. So this is the response for the sample questions using GPT-4 as also the input and the output uh, using this detailed description and then reasoning. Okay, that is fine. It's a low quality data, but I think it is good because GPT-4 has a kind of a world understanding inside the language model itself, um, which I think they tried to use here. But still, it will be limited in a way, as you can think, right? That is fine. So let's go to what the model actually used is. So architecture, the family goes to effectively leverage the capabilities of both the pre-trained LLM and visual model. The network architecture illustrated. So you can use like Llama, Vicuna, anything, which is the pure language model, F of this phi, uh, as it has the best instruction following capabilities in language tasks. Okay. So if you see here, we have an image here, right? And uh, you put that into a vision encoder to get the ZV, right? So let's open a OneNote. Mm, So let's say where's the pencil? Yeah, draw. So what they're essentially doing here is, so they have, let's say, LLM right here. We put this here. Yeah, so this is LLM, and what they're doing here is so this yeah, so ideally what they're doing is they have a vision encoder. One sec. Yeah, so vision encoder is like this, which is a clip model, right? Generally, it's a clip model. So you put the image into this, right? And you get like a latent representation of the weights, which is ZV, right? And ZV again, I think is used. So for the input image XV, we consider a pre-trained clip visual encoder, yeah, which provides ZV. So ZV equals to G, which is the clip of XV, and then this ZV again. Specifically, we apply trainable projection matrix W to convert ZV into the language embedding tokens HV. So every model, right, language model, needs to have uh, like it's converted into the vocabulary space, right? Uh, which basically is concatenated with the previous tokens also. So it has a context window, and what they are doing is they are using a projection to that uh, HV, which would represent a token specifically. And by the way, is like my voice etc. quite good? And by the way, yeah, seems good. So uh, that is projected into HV, which is basically represents the tokens, right? And so this basically is again put like there's a neural network here, one layer neural network. So like this, and it is projected to a different sized projection called HV, and that HV basically represents a token, which and then that HV along with let's say HQ, uh, this this can be like HQ1, HQ2 language instruction, right? And previous some HQ previous, right? So you can have this. One sec, let me do it properly. So HQ of previous context plus HV from the vision, and then HQ, which is the language instruction. This entire thing is the context window. So this is the context window, and this is then used for supervised fine tuning or instruct tuning of the model, right? So yeah, see, we consider a simple linear layer to connect image features into the word embedding space. Specifically, apply a trainable projection matrix W to convert ZV into language models. Yeah. So that is fine. And for the language instruction, they are using this kind of data set. And Flamingo Q form. Okay. What are they doing for training? Okay. Training tuning stages. So freeze both the vision encoder and language model. Train only the projection matrix W. So clip is frozen. The language model is frozen. We just need to learn, the projection matrix from the latent space to the token, which represents the language instruction properly. So I don't know how they, consider the the embedding space, the vocabulary, will it remain the same or increase? Or maybe I think H yeah, HV is not a single token, so it is a set of tokens. So I think the vocabulary is same. Yeah. So HV is basically a set of tokens which represent that image perfectly. Uh, right. So that the language model can work with only text as the autoregressive in an autoregressive way. So which is kind of cool for an idea. Um, so yeah, question answer pairs, then end-to-end fine tuning, trainable projection, vision encoder, frozen. Okay. Yeah. So the first stage they only train the W, and then they train uh, the both the LLM and the projection, which is cool. I think I will run this experiment tomorrow on stream, obviously, and let's see how like what are the changes in the the behavior. Let's see. Let's do that for tomorrow, and uh, probably the same time. And yeah. So is anyone there in the chat? No, is there? Hi, chat. If you want to ask questions or uh, give some ideas, which will be helpful for me also, uh, feel free to do so. And yeah, so I would want to recreate something like this, like a smaller version of this, just to understand how the you know how this fine tuning works. So yeah, this paper is quite simple in terms of what it's trying to do. But yeah, it was like the very start of the vision language model revolution. So as we tried the the latest 1.6 Lava Next, we can also try I think with the local images, or let's try something else. So a cat images. Okay, wait. VI at last. Let me try this. Ooh, yeah. So copy link address. Where is it? Yeah, there we go. And let me ask what is shown in the image here. Let's see. So I put the 3i Atlas image, right? It's loading the checkpoint shards. So it doesn't know anything about what 3i Atlas is. Keep in mind that because when it was trained, there was no images of 3i Atlas. So the image shows a stylized, elongated object that resembles a rocket or a missile. See, it is aliens coming, guys. It is a pointed front and a cylindrical body with some textures that could be interpreted as a rough surface. Okay. Lights are shining on it, creating a dynamic counter. The images are one second. Do you think this is a spaceship? Yeah. See, cursor also knows. Where did these images come from? Lol. Anyways. So yeah, it's being diplomatic here, guys. So this is nice. Um, that is nice. This is working. Let's just look at what their repository does. So do they have a training code for Lava train? So these are the legacy models. Ah, this is it. Oh, this is a different branch only. So is the training thing, yeah. So 8 A100s are required. My God. This is Coco 3 million dataset. Return takes 4 hours. 2 hours for 7 billion checkpoint model. So this is the training script. Uh, okay. We have used LoRa for fine tuning. Yeah, so this code is what uh, we'll have to look at how they're doing this. But one sec. So scripts, Lava, train, train.py. Yeah. Uh, F state. Tokenize function. Preprocess llama 2. Okay. MPT. Yeah. We'll have to look at this basically. So where is the serve, not serve, model? Yeah. Mistral projector. Okay. Where is the .sh file script? Yeah, here. So fine tune qdora.sh. Yeah. And where are the commands for this? So you do pip install. Okay. Install Python and Llava 1.5. So these are the training comps. Batch size 256. Okay. Where's the command though? Oh, just they just choose this. Training script with deep seed 02 retrain.sh. Okay. And Python and Llava. So, okay. Let's look at that retrain.sh again. Yeah, so they are using train mem.py and with these arguments, train mem.py. Let's look at that scripts. Lava train this thing. So we are using train with flash attention to um this monkey patch. Okay. Yeah, so this was the core itself, which is crazy good. I don't know. Yeah. So I think I'll end it today, guys, for this stream. We looked at Lava 1 uh, paper and also ran the Lava model locally, which is crazy to have like a 16 GB VRAM. No, not everybody has access to such big GPUs. Uh, and yeah, so thank you guys for checking the stream out. Do like if you like, and um, stay tuned for the next stream, which will be tomorrow. I'll stream daily now, and it will be on like using VLMs and games, uh, and different different, like for example chess or Valorant, which I tried before. But I think the field is ready to work with games using the VLMs and the vision angle action models VLAs. So there are quite interesting papers coming, and daily we'll do this. So stay tuned, guys. Bye bye, and sayonara. Peace.